Perfect. So I hope everybody's here. I hope to see a few faces at least. Thank you very much. Okay. For today, we will deal with function approximation in the context of control. So the brief introduction to today is, as always, the lecture will be divided in two parts, where we will sequentially expand on some concept. The first part will be dedicated to the first to the definition of the problem we are going to solve today, which is something a bit more complex, or at least a bit more realistic than the usual grid word. We will deal with cart pole, so it's a physics-based problem, and we will try to solve it in different ways. But essentially, first in the first part, we will use linear approximation. So we will see what it means, and we will see how it applied in a concrete way in two ways, with state aggregation and with polynomial features. Afterwards, we will do what is beyond linear approximation, in particular non-linear approximation with neural networks, which is essentially what is used in real technological application. And you will see a proper example of how it can fail when it's used just without using your brain first. But essentially, we will have just a brief description of what it means, how it use, and what kind of libraries are available at the moment for easy implementation. Okay, so first of all, I was saying that we want to deal with this cart pole problem. Cart pole is one environment taken from this library, gym library. You can find it here. It's the description. It's a physical problem in which you have a pole attached to a moving cart, but it's on a track, so the cart is moving. You have a pendulum, but it's an inverted pendulum, so the pendulum starts, the pole starts in a vertical position, and you have to try to balance it, just moving the cart below, left and right. So your actions are on the cart, but your reward is that you don't want the pendulum to fail. Before we describe it with numbers, I just wanted to show you a movie. This is a very famous problem, and all people starting reinforcement learning at some point we will deal with it. So they have also tried to solve it in a real context. For example, this user here has showed this brief video in which they applied a similar technique which we will apply, but with a real physical problem. And essentially, you can see that it's not an easy task. And okay, maybe I should remove the sound. But you can see what it means is that you have to move down. You have to move the cards below, and you have to try to keep the pendulum straight. Okay, so clearly it's a fun problem. It's a little less abstract than what we dealt with grid word, but in the mathematical implementation is very simple anyway. Let me go here. Code-wise, we just have we call this library gym, in which there are many of these environments. I'm just importing this cart pole here. You can see the true implementation in the code. You can find it here in this GitHub repository. But I just want to mention that the basic structure is exactly what I presented in the past lecture. So it's a class of some kind. This is a fake skeleton of a class, but you always have an init in which it's defined the proper physical world, so it's gravity, length of a pole, dynamics, not dynamics, but parameter of dynamics. Then you have reset, as we always seen. It's something which says, okay, start from scratch. Then you will have a step function in which you give an action and it provides a new state given that action and the current action. Then we will have a render, which unfortunately I will show you it does not work in my computer. So this was just to give an image of it. Then in particular, this class has a couple of things that I never used, just one seed for a random seed, and something which closed the environment. But I just wanted to show that this cart pole environment here, which comes from a library which has tens of environment, is of the same structure as we'll always see. So if you have something which works, an algorithm which works with a previous grid word environment or something, it will basically work also with this environment here. Okay, what is the state space of this environment? In particular, it's a box for object, but it just means that it's a four-dimensional vector of real numbers. These real numbers are as such. The first one is the position of the cart, and the second is the velocity of the cart. Okay. The third element is the angle of the pole respective to the vertical, and the fourth is the pole velocity at the tip. Okay, so basically the first two are for the cart, the second two are for the pole. Okay, so this is different from what we have seen so far, because so far we have always had discrete state space, but this is a continuous state space. So clearly we cannot implement directly what we knew so far. We have to find a new way, and we will see that within the context of linear approximation and nonlinear approximation, we can deal with such a problem. The action space is super simple. This is discrete. It's just two. It's just left and right. So you can act on the cart. You can move it left or you can move it right. And of course, you are trying to juggling this pole. For this reason, we will. Well, perhaps I can talk it afterwards. So the state will not be tabular anymore. We will have to deal with that because it's a continuous state. But the action is actually tabular. So we will separate our problem and we will do function approximation only on the states. The rewards, it's very simple. For each time step in which the pole has not fallen, I get 1 plus 1. But the episode is only 500. So whenever we find a reward of an episode of 500, it means that we have completely succeeded in not making the pole fall down. And the starting state is always something which is very close to a perfectly still position with a still cart and a vertical pole. But it's not, of course. Otherwise, it would remain there forever. Okay. The episode termination is if it's the pole angle is fallen above some 12 degrees, of which the position of the cart has fallen off the track. But this is also important. So more than 500, it's not possible. It will stop it anyway. It is considered in the reinforcement learning tutorial world that you have solved the environment if you manage to have more than 195 steps without making the pole fall over 500 consecutive trials. Okay, so we will see that we will sometimes manage that very good. Sometimes we will not manage to do that. This is how the environment works, but essentially it's like our environments worked before. So we have a reset function which to start. Then you just give an action, which is going to be 0 or 1, left or right, and it gives a new reward, a new state, a reward done, if the episode is concluded or not. It will give some info, but this we don't care. And of course, you can you can implement, as we did sometimes ago, like a fixed policy to see, but this is not interesting for us. Maybe afterwards we can play with it if we have time, but so right now, no. The only point which I'm sorry for is this usually allows us to see it on in real time with render, which so like movies like this. This is something which I will show afterwards. It's a very interesting post by Jean Zhu, which I will also link because it solves without reinforcement learning. But usually there is a movie for each episode. You can create a movie which is something like that. Unfortunately, my PC with Ubuntu and Windows does not manage to make it work. Anyway, let's go to that. Okay, so let's start. We have our environment. Our environment is this. It's very simple physical-based problem of a cart pole. We want to keep it vertical. The state is continuous for real values, so we cannot apply directly what we had so far. So we have to go in one direction, and we want to go in the direction of value approximation. So far, we had discrete number of states, and we have had a tabular approach. For each state, we could try to evaluate its value, or for each pair of state action, we could evaluate the Q value. Clearly, this is crazy in the sense that if the environment is continuous, we would not even know what to do. And if the number of states is very high, this means that you have to keep in memory a very large amount of information. And of course, since you have to visit each state many times to have a proper evaluation, you would have to have many trajectories. So we need to go over that. Value approximation is a simple recipe, which is very common. I mean, most common technique to do that. Basically, it requires two ingredients, or it consists in two ingredients. The first one is that given a state S, I need some way to construct an approximate value. So still it needs to do what it has to do. So given a state, I need to have a way to mathematically calculate its value. And I need to have a way to update this value given a state, given the usual experience. So essentially this, before I had a perfect mapping between a state and a value, now I have an approximate mapping. Before I had a rigorous way to update the value given our trajectories, now we want to create what is the equivalent of that. So in value approximation, to calculate the value, we will use an auxiliary weight vectors W, such that now the value function is a function of both the state and of this weight view, W. So we will write like this or like that. And essentially, this auxiliary vector contains all of our knowledge so far for the value, okay? So at a given time t, I will have, instead of having the values written somewhere, I will have a weight vectors written somewhere. And from that, I will be able to calculate the value. And since all information is in this vector here, also the update will not be on the value itself, but we will be on the weights. Okay, so every time I have an experience, I will be able to change my parameters auxiliary weight vector W, so that afterwards the value will change. And as we saw before, the value usually changes with some update like this in temporal difference. So I had some estimator delta, and then I change my estimation of V and Q. Now I will have my W, my auxiliary vector, and the change is very similar, but instead of changing the value itself, I will change the gradient of the value in respect of the auxiliary vector. So it's an indirect change. Instead of changing directly the value, I'm changing the value through the change of this auxiliary vector through the gradient of the value function respect of the weights. Okay, so this is extremely general, which means that we are not dealing with the value anymore directly in a tabular sense. Now we are dealing with some weights, which for now do not mean anything. We will see that there are, in the linear approximation, the weight will have a very simple meaning. So in linear approximation, first of all, we have to, instead of using the state S, we will use, we will write this state in a sense in a basis which are of features. And the features are different, let's say, in a sense, different property of the state. And the features will live in a different space with dimension D. And will be real numbers of dimension D. So it's just so for each state, I will have the D real values, which will correspond to the features of the features component of that state. This seems complex, but it can be understood in a very simple reason. For example, the state could be a house. The features could be the number of baths, the number of rooms. Okay, so the house is a very complex thing which contains a lot of information. The features will be how many baths is there, how many rooms are there, and of course for each house you will have small numbers, which is, for example, a house could have 3 rooms and 1 bath. So 3 and 1 will be the feature vector of the features, which are how many rooms, how many baths of that house. So it's a way to connect the state to a vector of real valued numbers. The good thing is that normally the dimension of the features, which is called D, can be extremely smaller than the dimension of the space. If the dimension of the space is all houses in Trieste, then gonna be thousands and thousands. But if the features are only the number of baths and the number of rooms, then this dimension is only 2. The features are an extremely important part of the game, and clearly they are a double-edged sword. So if you choose the features very well, then everything is simple. If you choose the features very poorly, then everything is almost impossible. But once you have the features, which is an extremely important part of machine learning, reinforcement learning, but once you have the features, linear approximation says that then the value can be approximated or is approximated by just a sum of some weights multiplied by the feature. So it's a linear combination. It's a linear it's a linear function of this feature here. Okay, so this is linear approximation. You have your state, which is described by some features, and then you just multiply those feature vector by some numbers, and you have the value. Generally speaking, this can be done for both the state and the action. We will, as I said, since the state is complex because the state is continuous positions, angles, and etc., but the action is just left and right. What we are going to do is that we are going to do linear approximation in the states. So the states will have corresponding features, which we'll use to calculate the value of approximation, but the action will be just 2 different sets of states. So when I want to calculate the value for a state and an action, I will take the feature vector of that state, and I will multiply by a set of weights, which correspond to only that action. So I will need to store 2 different weights for the action. So this is a simpler way of dealing with it. Okay. To recap, the basic idea of linear approximation is that I have a state, I choose some features, then the state has feature vectors in these features, for example, number of beds, number of rooms, etc., etc. And the value is a linear combination of this feature vector x of s. Second thing we'll discuss briefly is that to choose the feature is extremely relevant to how well the reinforcement learning will perform. Good. If you have questions so far. Okay. Then we will deal with the most simple linear approximation, which conceptually at least, which is state aggregation. State aggregation, it means essentially that if the state space is, for example, like this, continuous or too detailed or everything, then instead of dealing with state, we'll be dealing with regions of state as our unit elements. And so we have the features which are regions of the state space, and the feature vectors will be just a series of 0 except for a 1, and the 1 corresponds exactly to that region in which the state is. Okay, so we have divided the space, we have a single state, and the question is, where is that state in the region 3? Okay, then you have a vector in which everything is 0 except for the position 3 in which I have a 1, which says I am in that region. Then the implementation of the algorithm is extremely simple. Essentially, it's the same. For example, this is using SARSA. It's the same thing. You have a state, then the state is mapped in its a feature vector. So essentially, you have to find in which region it is. You calculate the value using the approximation, linear approximation. Then you use this linear approximation of the value to select an action. You use an action, which brings the state into a new state and gets the reward. Then you have the new state. In the new state, you can see in which region it is, and from which the region in which it has fallen afterwards, you can get an approximate estimate of the value function. Okay, essentially, you still work in states, but the states are mapped into regions, and you only have values for those regions and not for the states anymore. Why is it extremely simple? Because as you remember, we need the gradient of the value function in respect of v, and we can check very simply. So if the value for a state and an action with a auxiliary vector w is just the sum of these weights multiplied by the feature vector, if the feature vector is just everywhere 0 except for a 1, and that 1 is the one corresponding to the region in which our state it is, then the value function is actually none other than the single entry of the weight vector corresponding to that region. Okay, so formally we have that the value function is a linear combination of the weights and the feature vector, but actually it's just that it reduces to just one W. When you do a gradient of so a derivative for W1, W2, W3, and you have only just Wj, it means that the gradient is actually a series of 0 with just 1. Okay, so formally it seems very complex. In reality, it's basically that instead of working with SARSA in the single state, you're working SARSA in these regions of state. Okay, so state aggregation means you're making a coarse-grained state space of regions, and you work there, essentially. One of the simplest way, then you have to construct the regions, and you have to construct the way to implement the state into map the state into a region. One simple way is bindings. We all know how bindings work. For example, if I have 2 dimensions, S1 and S2, then we can have some divisions along the 2 directions. For example, we have 3 states here: red, orange, and green, and you can see that there are 3 different states, but actually they are only in 2 different regions. So this red and orange will share the same weights. Okay. Clearly, you can do it many ways. For example, you can decide that one dimension is irrelevant. So essentially, you aggregate all states in that dimension. For example, I'm considering that S1 is important, so I want to keep S1 different from one state to another, but I said that S2 is actually completely unimportant. So two states can be very close in a metric sense of S1 and S2, but or very far, but actually they can be aggregated in a completely different way if my state aggregation is different. Okay, as I said, formally, we have that the vector of features is a long series of 0 with just 1. In this particular sense, maybe, for example, here it would be 0, 0, 0, 0, 0, 0, except for here. It's a 1D vector of features. Sometimes it's easier to construct it as a matrix, but it is 1D vector of just features with 0 and 1s. And the weight vectors at the same dimension. So again, it's a 1D vector with auxiliary weights, which contains the current estimation of the values. Okay. So formally, you are doing a linear multiplication element-wise between the two. And so you are doing a lot of zeros plus one value. But clearly, in the practical implementation, generally, you just have some vector of weights, and you choose the index which is relevant to the region you are considering. Okay, so formally, you are doing a lot of zeros and a lot of multiplication with 0, but practically, you do state aggregation and you deal with regions instead of one thing. In a sense, we could do state aggregation without changing what the algorithm we had last time. If you do state aggregation outside of the reinforcement learning, if you have your, for example, you have your, in your episode, you get the new state, and instead of giving to this state to the reinforcement algorithm, learning algorithm, you give the region, then the reinforcement learning should not even be changed. It can work anywhere, anyway. Okay. I wanted to present a proper implementation of it, which is a bit useless, but maybe it's a bit, it shows more clearly what is happening. So we create a new version of SARSA in which we are dealing the things properly. So we have to store the weights instead of a Q value, but the weights are the Q value in a sense. We need a way to perform the state aggregation. So we need a function which takes the state and reproduce a vector of features. And we need a way to compute Q with linear approximation. So doing the proper multiplication of the feature vector with the features of weight. Okay, so I will add it inside the class, but I just wanted to share it because this is one new thing. This is something which is just a state aggregation function. It takes a state, it takes the way the state is should be binned. So binning is just the it's an array. I can show it here, for example, one. Okay. For example, it's an array of 4, and you have the lower bound and the upper bound of each dimension. This is binning. It's just the bounds of each dimension. And n binnings, where it is, sorry, I apologize for this. N binning is just the number of regions in which each dimension should be divided to. Okay. Then I have to create a vector of feature which is 0 everywhere, and I have a vector of indexes which is 0 everywhere. Okay, to keep track of where the single one will go. Then I take the state. I take each of the 4 dimensions which are real number of the state, and I just do the binning. If a state is below a lower bound, I put it in the first box. If it's above the upper bound, I put it in the last box. And if it's in somewhere in between, I just do the normal binning thing. I take the state, I shift it by the lower bound, I divide it by the total dimension of the bounds, and I take which index it is. At the end, I have a vector space which was everywhere 0, but now I have at a single place, I have a 1. Okay, this is a very complex thing to get a single one from the beginning. Does it work? So now, okay, now I have my state. The environment is cart pole, so this just returns the starting state. I'm printing, so this is the state, so it's 4 real numbers very close to 0. And then if I ask the state aggregation in these simple rules, for example, I'm asking a binning which is actually asymmetrical. Let's do 3, 3, 3, 3 or something. Then I can ask, okay, if the binning is 3 in each dimension, what is my index? My index is 11101. So the proper x is it's a matrix of everywhere 0 except for a 1. Properly, in the real sense, the feature vector is a series of zeros with just 1. Okay, the fact it's a matrix, it's for practical use, but formally, this is the feature vector of the state S. Good. So I hope I have not lost you so far. So essentially, the SARSA for state aggregation, it's a very simple modification of SARSA, which requires only the binning. So it's the same. So instead of gamma, you have get gamma. Instead of space size, now I call it feature size. Now I have some information to do with the proper binning. And now instead of having the storing the tabular value, Q value, I'm storing the tabular weights. So I used to have self Q values equal to n bit 0 of state space action size. Now I have this weight vector that I'm saving. Then I have the function state aggregate, which is the same as I showed before, which takes a state and returns a proper feature vector of all zeros except for a 1 and the indexes where the 1 is. And then the single step update is actually super simple. So I get, it's a SARSA, so I have S, A, R, new S, new A, state, action, reward, new state, new action. But I'm not working the state anymore. So instead of the state, I'm asking for the bind, so the feature vector X, and actually the index is where the 1 is. And instead of working with the new state, I'm working with the new feature vectors. So where at the beginning I had the delta Q was the reward minus the value. Formally, I should do that the delta Q is the reward minus the dot product of all the vectors X and all the vectors Y, element Y, W, element Y's, which in Python it's this strange thing, tensor dot, it means that it sums over all the axes. Instead of doing that, I just do the delta Q equal to R plus 0 minus the weight at the position of X index. And you can see that actually this formulation here and this formulation here are essentially the same, but I'm not working in the space of S, I'm working in X. If the episode is not done, then you have the basic thing. You used to have R plus L gamma Q values in the new state, new action. Now I have R plus L gamma W new X new action minus W in X in action, and you used to have minus Q values of S and A. Okay, so same thing as before, but instead of working in S, I work in this state aggregated space. And then the update is essentially the same. It used to be that Q values plus learning rate multiplied by delta Q. Now is formally, again, it's a multiplication of the learning rate, the delta, and the vector of features, which are everywhere 0 except for a 1. So in a practical sense, it's just an update of a single entry of this V a vector, which is just like that. Okay, basically the same. How to get epsilon greedy? Again, we are not working anymore with Q values in a tabular sense. So I have first to get the aggregate state, but then I can easily calculate the Q value approximate. Okay, but where this was the Q value for a single state in a tabular sense, now this is the Q value approximate for all the state which have the same feature vector X. Greedy policy is the same. So, Starsa in the most basic sense. Now, before we had nothing we could choose. Whoops, let's do 1000. So now we are doing a binning which is a bit. Let's say I have no idea what my system should do, so I'm starting with a binning of which is uniform. Let's do it. Perhaps it's even numbers are simple. So I have for dimension, I have to decide. So these were unbounded, most of them, but I want to keep it restricted to the small region. So let's do minus 0.5, 0.5. I have 4 dimensions, so I want to have some choices, but not too much. So I will have 4, 4, 4, 4. And you can see that if you have many dimensions already, this number is incredibly large. So 4, 4, 4, 4, it seems very poor discretized version of the state space, but it's reasonable. It's quite a lot of numbers. Okay, and then it's always the same. I'm initializing my algorithm. I'm keeping track of the performance. I'm doing convergent, like a decaying learning rate and epsilon, and this is exactly the same as we have always seen. Okay, so clearly this is sorry, print e and apologize. Yes, I understand, because this does not exist anymore. Okay, you can see it's quite fast. I asked for 1,000 episodes. So we have time for a question if you have one. As always, I'm trying to be as modular as possible in the reinforcement methods and environment. This means that everything is extremely slow. So if you are trying to do a technological implementation, I advise to change basically everything. And we will see afterwards with neural networks, it will be like the worst use of neural network you will see around for years. But it's just for teaching. Okay. Very good. So you see what happens. Actually, it takes 1,000 episodes, but it reasonably well understands and finds the correct solution. It means that at the beginning we had very noisy. Remember that this is each of these numbers is the number of steps in which the pole did not fall. So at the beginning, with less than 100, it was doing random things and it was falling off. And remember that the definition of solution is that for 100 consecutive episodes should be above 195. So perhaps we managed to do that, perhaps not, but still it's quite clear that he managed to find a rather good way to solve a solution so far. And so we did another coarse binning, and it worked. Okay. Of course, one say, okay, this does not solve it perfectly because the binning was too small. So let's try to go higher. Okay. And we will see that actually, most probably the result will be not what we expect. So if I have a higher binning, it means that the system is seen more detailed, okay? So it can differentiate better states in which should do one action instead of another. But it also means that the number of parameters in which should learn, it's much higher. For example, if I went for 4 to 5, to 4 to 8, so twice, but I had 4 dimensions, so I had twice, okay? And actually, even if the description of the state is better, so it's more detailed, it can resolve the system better, actually the performance is much worse. It almost never reaches 500, and it for sure has not 100 consecutive episodes above 195. So a very nice thing which I found in this blog, which I showed before and I will show again, is that if you take this, so for example, let's do a bit of physics. So we have a cart moving with a pole, and we want to balance the pole. So first of all, do you think that the position of the cart is relevant? Perhaps no. Okay, and then if you have some small physical idea, it actually the idea is that, for example, if the pole is falling somewhere, then perhaps you should also move it there to balance it out. But also that if the pole is moving, maybe it's the orientation of the pole, it looks like it's falling, but I have a velocity and I know that it's moving like that, then perhaps I need to stabilize in the other direction. So with very few physical consideration, we arrive to this super strange binning here. So the binning now is super coarse. It's just, I don't care about the position of the cart. I don't care about the velocity of the cart. And I strangely care about the other two dimensions. And we will see if I'm not completely wrong. And I hope I'm not. So I'm using even less episodes. So I may be wrong completely. Okay, less episodes is not sufficient. So let's go back to, I apologize. And I hope it works. Otherwise, I would make a fool of myself. Please let it work. So now okay, it has not, you can see that something strange is happening. So actually, it has found many times a perfect state, but the system has not converged. Anyway. Okay. Okay, I will answer the chat. Please, when you make the question on the chat, please tell me before, because I'm not always seeing it. So I will go back to it. Okay, perfect. So I will put 2,000 episodes, and then I will talk about the two questions. The first question was, what is the feature for the cart pole problem? Okay. So now the cart pole problem, the state has 4 real numbers. So the state is it's given like here. The state is composed of the position, of the cart velocity, of the pole angle, and the pole velocity at its tip. Okay, this is the state. The features is what I want to consider. In the case of state aggregation, the features are the regions which I'm considering as a group. For example, if I do this some binning, okay, let's consider only in one dimension. I have one dimension. I have a continuous from 0 to 1. I have 4 bins. The features are: am I in the first quarter of the bin? Yes, that is my feature. Okay, the feature is, am I there? Okay, so in state aggregation, the features are, do I belong to this region of state space? So the state are 4 real numbers, and the features are the discrete, the belonging to a region in this 4th dimension of space. Okay. Then the I hope this answered the question. Otherwise, maybe we can talk a bit in the post. Okay, perfect. With 2000, we see that it has perfectly learned the solution. Okay, I just wanted to show. Why is the reason of this binning, I changed the bound here. So it turns out, and this is shown in this very nice, you can find I will send the link, with How to Beat the Card Ball Game in 5 Lines by Jean Zhu, that actually the solution from a physical point of sense is just that you want, when the angle is small in amplitude, you want to stabilize the angle. So you want to try to make the angle as small as possible. But when the angle is large, no, sorry, when the angle is small, you want to go opposite to the angular velocity. But when the angle is large, you want just to try to put it as close to 0 as possible. Okay, so since we only care when the angle is small, I actually created this binning here. So 3 binnings, it means that there are 3 binnings. One binning is from -infinity to -0.03. The second binning is from -0.03 to 0.03. The third binning is from 0.03 to infinity. Okay, so this, I changed this bin because I only care, there are actually only 2 situations I care. Is my feature to be inside of this small angle range? Yes, no, or no. Okay, since my policy is the policy which is from a physical sense, so this is not a reinforcement learning policy, this is a policy created by ad hoc. If this policy, if I'm able to distinguish these 2 positions, then it's enough. And why I did a 2 binning there? Because this is the velocity of the tip, and I just need to know if it's negative or positive. So this strange binning here actually is able, in a minimal sense, to see if the angle is very close to 0 from this binning here, and if the pole velocity at the tip is negative or positive. And this is sufficient information from the 4-dimensional real numbers which I had as a state to create a perfect policy. Okay, why is it nice? This because it means that the problem is actually very simple, but you have to solve it beforehand to actually use the proper state aggregation, which makes it very simple to solve even in reinforcement learning sense. So the message here is that the first thing I could do is just, okay, the lower bound, I will take the lower bound, since the card could go everywhere in the world. So the lower band is -2000, the upper band is -2000. I want a very detailed scale. So I will put that the first dimension is 500 beams. Okay. This is like the brute force approach. I want to create a state aggregation which is as detailed as possible. This will never work. If you have a physical intuition which you can put into your state aggregation, it will work much better than if you put as much detail as you can. Okay, good. Are there questions so far? Otherwise, I can go fast into linear, maybe not too fast, in the polynomial features.
May I
yes.
comment on this? Because this is very useful as an example. It's also very important. So it's important to compare different philosophical approaches to the problem of function approximation. So linear approximation is good because it's explainable, it's transparent. Okay, when you construct such an approximation, you get what you put in, especially if you select manually your features. Okay, and of course, the operation of selecting manually your features must be guided by some expert advice. So this is the point where reinforcement learning makes connection to a branch of machine learning, which is now not very popular, but was extremely popular in the 80s, which is expert advice. So to construct databases or collect data of experts which can make suggestions about the way you should make decisions. So this is a great example of expert advice in the sense that Emanuele has been looking for expert advice. He found these nice suggestions and he chose the features suitably and was able to reduce your infinite state space, okay, a 4-dimensional continuous space into a handful of features and to solve exactly the problem. A brute force approach, like I just said, in which you try to discretize, would have failed miserably. And you can check it, it does fail, right? As you have seen. A machine learning approach in which you try to automatically find the features might or might not work, okay? So you might ask the question, can I learn this representation? Can I learn these features? So there are techniques which address this problem, but they depend on the data set on which you perform your training. So for instance, if you produce data with a policy which is bad and the pole always falls, you never realize that this is a good set of features. Okay? So also automatic constructing your features might fail if the way you collect the data is not informed itself. So you might think that there is less expert advice, but there's always a little bit of expert advice. So this comment is important because I think it's a sort of an existential comment for those of you, especially for those of you who come from other backgrounds than pure computer science. There is a meaning to be a scientist, okay? So there's a meaning to add knowledge into machine learning and not to just to think of taking a completely blind black box approach. Okay? There is value into this. There is opportunity of solving extremely difficult problems if you put knowledgeable input into your problems, okay? Thank you.
Okay, so perhaps we better have a small break now, and then restart in 15 minutes. So if you have questions, or okay, I will pause the recording. Okay, let's start again with the second part. So first of all, we're going to deal with polynomial features. So far we've seen the feature which were state aggregation. So whole parts of the state space were condensed into a single entity, a single region. Now we're going to deal with something different, which is how to construct polynomial features. So in this particular case, it's simple because we have a state which is already done by a vector of real numbers. So we could construct some features which are just a polynomial expansion of these real numbers which constitute the state. So for example, we could have some matrix multiplication, and when we have it x, it's a vector made by a linear combination, then quadratic combinations of these components of the state. In particular case, we're doing a very special one, which is a polynomial only in name, because it's going to be linear in the sense that we are taking the feature of the state exactly as the values, the coordinate in real values of the state. So essentially, our new feature vector will be identical to the state. Okay, but we could have taken, for example, we could have expanded, instead of only having the 4 real numbers, we could have the 4 real numbers and then all the pairwise combination, for example, S1 multiplied by S2, S1 multiplied by S3, etc., etc. In this case, we take the simplest one, which have that the features are the state itself. Let's recall that the features are the position, the cart velocity, the pole angle, and the pole velocity. Okay, so the first two to the cart and the second to the pole orientation. Then the value, the approximation of the value is a linear approximation of these features. In particular, I will have to store a vector W, which is only 4 real numbers, and the value approximation is going to be only that the inner the dot product between the weights and these 4 real numbers. Okay, so the whole method is that I took a polynomial features, but right now I actually took exactly a linear combination, actually the identity over the state, and I'm going to multiply by 4 values, and for each state I will just determine the value as this linear combination here. This is extremely limiting, and we will see that since the problem itself, the dynamics are not linear, then this is a very stupid idea and it will fail. But just to point out that this is a way to do. Once the feature calculation is done, the control algorithm is exactly the same as before. So I will very rapidly go over to it. So we have to save this weight W, which are actually only 4 values for the action left and 4 values for action right. Then the polynomial features of the state is just the state. Okay, and I'm leaving here for exercise. If you want, I also almost put everything you need to do, at least something which is slightly better than this, which is going to a full second order polynomial features. Okay, so you see here I commented it, but you can construct a feature vector which instead of having only S0, S1, S2, S3 has also a 0 order and all combination of second order. Okay, in principle you could add all combination of third order. Okay, I'm going to deal right now with solution only using the first order of the polynomial features. But this is before I had state aggregation here of only polynomial features, but again I only produce X. Then the single step update now is done with the with only this very simple thing here, which is the equivalent of the formal definition. So the Q value approximate is the dot product between the vector of the weights and the feature vector. Like the Q values in the new state and the new action is the dot product between the values, the weights in the new state and the new feature vector. But everything is the same as before. And then right now, it's not a single update, but I'm updating all the matrix of the weight vector with this. Okay, depending on the feature vector, I'm updating the weights. Okay. The definition of getting action epsilon grid is the same because again, what I need to do is just select the feature vectors and then construct the approximation of the value and then everything else. So it's essentially exactly the same method as before because it is the same, exactly the same method. So linear approximation, but now I change the feature vector. So this means that whatever strange feature you can cook up, if you have if you add a function which takes the state and returns the feature vector, this works because this is by definition the linear approximation. How you construct the feature vector is something else. I just wanted to show that now I already run it, so to make it fast, I'm using the same parameters as before, the same number of episodes, the same environment, the same everything. I did 2,000 episodes just in this short time of a break, and this is the result. The results are consistently around 40, and 40 is by definition what you get with a random policy. So if you take a drunk person and you say, please try to keep this inverted pendulum vertical, basically it works as a linear approximation with polynomial feature of first order. Okay. Again, why? Because the first order polynomial feature is it's a poor way to construct features. Which is good in the sense that this is if you want to construct the feature in an intelligent way without resorting to machine learning, this is one idea, is that if your problem is non-linear, then you should have features which include this non-linearity. Okay, but this was just to show that the linear approximation method is it's very general, and it's separated from the way you construct features. So you construct features, and when you have that, linear approximation just means that the value approximation is it's a linear combination of those features with some weights, and you have to update the weights and not anymore the Q value. Good, let's go beyond linear approximation. So this is what is done normally, and it's something which has achieved an incredible success, especially in the last few years. When you, especially now, the new iteration, the new results are such that you do not, everything is done with machine learning, in the sense that there is no this expert advice. There is the new iteration of AlphaGo and everything actually do not require any expert advice, and they consistently are performing the best. We will show that if you are not able to reach that technological sophistication, it will not work without an expert advice. But the idea is that we are going in that direction. We are going in the direction of neural networks. So linear approximation was that once you had the features, you had only one way to construct the approximation of the Q, of the value, which was a linear combination. Now you can use whatever you want, and will have to be a parameterized function with some weights which parameterize the function to be the best description of possible of the value. We use neural network because neural network has been proven theoretically, but also in a practical sense, to be very well behaved universal function approximators. They can, in theory and in practice they do, reproduce any given functions with some parameters inside which have a space which can be very large, but still they are in a sort some fitting function with the weights as parameters. They have many different types, but essentially they share most often some particular architecture type, and also one of the most important features is that they have to have some degree of non-linearity in them. Okay, why do I call them fitting function? Because essentially what you want to do is minimize the value error, as you know from theory, which is, for example, the expected value if you follow a policy of the value of a policy you are currently estimating minus what you are using as an experimental value. So this could be the return or whatever, minus the your current estimated value depending on the weights. Okay, so this is a function. This is like a target value, and you want to minimize the distance between what the output of the function is and what you want to get, the target. So it's basically a fitting problem. How do neural networks work? So I just want to go in the shortest possible through the basics. Generally speaking, they have a structure which is rather linear, in the sense that perhaps linear is not the good word, it's directional. You start from a vector of input x, you go through internal what are called layers of so consequential groups of operations, and then you end up at the end with an output which is your evaluated function output, and then you have to compare it to a target result. Usually speaking, the first and perhaps most common to start is the dense layer, which means that so each of these edge you see correspond to a weight parameter, so it's a real number, And each of the nodes correspond to an operation. In this case, it's a simple operation which connects. For example, you can see H2 or this node here takes a linear combination with these parameters of the input, like something like that. And then, so this is a linear operation, so a linear combination of all the weights, which are the parameters which will change of the neural network. And then at the end, it will do, generally speaking, a filter, a nonlinear filter. So, for example, H11, what will happen? It will happen that it will have some sum over all the input multiplied by all the weights plus some other parameters which are acting as a bias. We'll get a number, and then after this number is taken in a linear way, it will act with a nonlinear function. These are two very famous ones. The one above is a sigmoid. So essentially it takes whatever it has before and it returns something, a new number, which is between 0 and 1. Okay, like an activation function, and this clearly breaks all the linearity which was before. Or a very common one which is used now is called ReLU, which is a nonlinear function which returns 0 if the number which has got as an input was less than 0, and the number itself if it's above 0. So this is a 0 everywhere, except if it was a positive number, then it returns the positive number. So each node takes the information of the previous node with some weighted with some parameters of a neural network, computes it, and then use the nonlinear filters, and then pass it on. Okay, so this is the reason why you have these layers. Each layer works only on the previous layer. Each node computes a number and pass it on to the next layer, which each node computes an operation of the previous layer, and so on and so forth until you have reached the end. So a neural network is a collection of, it gets to millions of weights of different values W, and inside it can have thousands and thousands of individual operations of this addiction, with sums, then with nonlinear filtering, etc., etc. But it turns out it is very convenient to use, and there are essentially two reasons why it's that. It's because even if it seems crazy that it's not difficult to get the gradient of this function here with respect to the parameter, it's actually a rather straightforward thing. Because we can use the chain rule of this differentiation. So since each of these operations happen sequentially, you can actually go through the gradient from the last part and separate each individual part. So all nodes not only have can use to construct the function as it goes on, but also can construct its gradient depending only on the layer, on the closest layer. Okay, so with using the chain rule and the backpropagation, actually it's very simple to construct the way to update all the weights. What it means? Okay, so the neural network produces some values which are our prediction of the value. Then we have the target. Okay, these two numbers will not be the same. So we will define a loss, so a distance between what I have predicted and what I actually wanted to come out from the neural network. And then I can, since this is a sequential part of nodes connected one with each other, I can easily construct the derivative of the gradient of this loss respect to the first layer, and then the derivative of what I got in the first layer depending on the second layer, and then the derivative of what I got in the second layer depending on the third layer, and so on, so on, so on, and so forth. And then I can construct the update for each individual parameters just as a combination of all these small tokens of gradient which I constructed before. Okay, so it's rather simple because even if it seems like a massively complex object of operation, one inside another, actually, I can use the fact that the gradient is very simple to calculate from one layer to another to say, okay, I got this number, I want to be this number to close to that number there, and then I can change my local gradient propagates backwards into the neural network. Okay, all of this to say that this simple fact that it has a simple structure, and then all the nodes act only on closed nodes and in a very closed and like separate ways. So it's blocks of operation. It makes so that it's easier, actually, some straightforward, if not easy, to construct the gradient, and so to construct the update with it. Okay, how do we use it? Generally speaking, nobody writes neural networks anymore from scratch because there are wonderful tools online. I will use this library Keras, which is rather common. It's written to be very simple to visualize and use. In particular, I will construct what is called a sequential model, which is basically something like that. So I will have just a straight sequential structure of layers. And this is all that it is to define a neural network. So I say I want this neural network to be a sequential model. I want to add a first layer of 20, given that the input dimension will be 4, which means I'm taking an input of 4 and I want to construct a layer of 20 nodes. And these 20 nodes each interact with this ReLU, which means that all of these nodes will be connected with weights to the input numbers, will combine a linear function of these weights and the input numbers, and then they will apply this ReLU nonlinear feature, all of these 20 nodes. Then I want to construct another layer of 20. So all of these 20 nodes will be connected with weights to the first 20 nodes, again with an activation of ReLU. Then I want to construct, for example, 2 as an output, which means that this layer here will be connected to the output 2 nodes, which will be just a linear activation. So we'll take a linear operation of the 20 node before. Then this is compiled. It means that I'm constructing more or less the neural network, saying that the loss, so how it, what kind of error you want to minimize is MSE. So the one we want here. And the optimizer, so the way it does is SGD, so stochastic gradient descent. It means just how, when you have the gradient, how to apply. And this you can, you don't need to know. So, and it constructs everything by itself. Did I import Keras? Yes. Apologize, I could have left.
Can I ask one?
Sure.
So we use the neural network to extract the features.
Sorry.
We use the neural network to extract features.
Actually, no. So in this particular sense, we are using again the state as the feature. So you can think of it as the features of the feature are the state, and then from those features, instead of having a pure linear function, you are using the neural network. In principle, you could do feature extraction with a neural network. It's something else, but in principle, you could have another neural network that takes the state and produce the features. but we are dealing with the part from the features onwards. Okay, so we are dealing with the fact that our feature vector now is exactly the same as as in the case of the linear approximation. So it's the same thing as here. I apologize. We are dealing with polynomial features with only first order. So we are at this point here, but instead of using this linear approximation for the value, we are using this non-linear approximation for the value. Okay. Okay, perfect. So yeah, constructed the model. Is it fine with this question?
So the four input are the position, velocity.
Yes, exactly. But in a yes, exactly, yes. But for example, they could be state aggregation. So I could do state aggregation of those four. So I have a bin vector of all 0 and 1 and give that vector to the neural network. It will probably not work that great, but I could do it because the two things are separate. The feature on one part and the fact that we want a non-linear approximation from the features to the value.
And the feature is from negative to positive values.
Yes.
But here you use ReLU for the activation.
Yes. The ReLU for the activation provides a positive value, but the parameters could be negative.
Mm-hmm.
Okay. So, for example, H11 will always produce a positive value, but then W21 could be -1. So this positive value could become a negative value in the second activation. And the last layer is linear, so it does not have this ReLU. So it could be negative or positive or whatever. Okay.
Okay, thank you.
Thank you for your question. And okay, so I created this simple neural network to show that there is this simple summary function, which just shows that the fact that we have created a model in a sequential way. We have this description. It says I'm starting with a dense. I have 100 parameters only to get to the first layer. I have 420 parameters from the first layer to the second. I have other 42 to in final. So very simple neural network already has 562 trainable parameters. Okay. Then, okay, this is essentially what I'm going to do. I will do something that I will break everything, but I already apologize. I will remove this. No, I cannot. Okay. Okay. Just okay. Good. So we have this is the same class as before. It's the SARSA, but now we will have a neural network to approximate the value. Exactly the same as before. So we have gamma, we have our input size, we have an action size, we have a learning rate. But now for each action, where usually we had a storage of tabular values W, or we add the components, now what we have is for each value we have created one model, which is a neural network. Okay, I created a very simple thing. This is 1. The last output is 1 because this won't be the single value for that action given a state, but the state will be an input. So the input is the state. first there is a 20 layer in the 20 nodes in the first layer, 20 nodes in the second, and then the last one will be just one value, which is the value of that. And I will try with optimizing with this method, which uses the stochastic gradient descent. Then the single step update is that I get a state, I get an action, I get a reward, I get a new state, I get a new action. Now, I've just modified this to in a sense, answer your question, which now S is the state, X, which I needed to reshape because the neural network, instead of a vector, it requires a vector of other dimensions. So this is a technical issue, but I'm calling it X, okay? Because even if it's the state, we are dealing with as it is the feature vector, okay? So this is the feature vector of the state S. This is the feature vector of the state S prime, the new state. Then I'm applying the neural network at position given by the action to X, to the feature vectors. This does what? These simple lines here tells us to give X as an input, and it automatically by itself, this method takes it, does all the operation in the first layer, all the operation in the second layer, and returns only the last layer, so the output. Okay, so by doing this, I have effectively used the neural network to produce the approximation, nonlinear approximation of the value given the feature vectors. And then I do it also for the new, for the Q in the new state and the new action. And then where I used to have the delta Q, so I was already doing the update in delta, now I want to give the target, okay? So the delta was R plus 0, which was the target, minus the value of Q, okay? Actually, since it's already implicit in the construction of a neural network of scaras, which it will try to go towards a target, instead of saying that the delta is this, I'm saying your target is the first part, R plus 0. Your target is R plus gamma multiplied by the new gamma, new Q, okay? And then I take the target, I reshape it because again, this neural network requires a certain shape of the vectors. And then let me cancel this, which was just, it's cluttering everything, okay. This is, I taking the neural network corresponding to the state, to the action I took, and I'm using this method fit, which just means this is your input, X, the features. You already know what it will end up with a neural network because you can calculate. This is the target. Try to minimize it, okay? And since I have not put anything, this means that he will take only one instance of X. He will try to match it with the target. He will construct automatically the gradient for all of the internal weights, which are 562 or whatever. And then it will follow the gradient one step with the learning rate we gave, okay? Which is not ideal. Yes.
Sorry, I didn't understand why we have a neural network for each action.
Good question. So we are dealing with SARSA, and we are still using a tabular method for the actions. So SARSA, what does it want to do? SARSA want to have the Q value for each actions, and or an approximate value of a Q value for each action, and then choose the Q value which is best, or do an epsilon and greedy policy on that. I could have done that as an input of the neural network was also the action, okay? And then I could have done that the approximate value of Q given an input X and given an input A is this, given an input X prime and given an input A prime is that, compare it. I could have done that, but so far we are using a step below, in which for each action separately, like in a discretized manner, I'm using value approximation. So I do not approximate the value given the action, because for each action I'm approximate only in the state space. So this is value approximation in state, but not in action. Normally speaking, all of the thing you can find in tutorials, everything, will have a value approximation in both actions and I mean value approximation not in this tabular way. But I wanted to present as a first step that you have different value approximation, but the action space is perfectly separated, which is fine in this case because Scarpola has only two actions, left and right. So I just need to save two things. If the action space were more complicated, then it would not be a good idea. I hope this answers your question, but it
Yes.
was very important. So thank you very much. Okay, so everything else is the same.
Excuse me.
Yes.
I have a real question for
Yes.
once. So could you also have done a neural network which has just states as inputs, but as outputs the vector of values labeled by actions? Q1 and Q2 as outputs.
Yes. Yes. Yeah. I wanted to, in a way, I wanted to be modular in the sense that since I kept two tabular weights here and there.
I understand the reason. The question I'm asking this is that you expect, I mean, if it works, you expect this neural network to discover, there's two different neural networks that you have to discover the same description of the states for it to work, right?
Yes.
So there is especially the first layers hypothetically should converge to the same weights because they want to describe the state space in the same fashion. And then only deeper layers then would decide whether it's good to take one action or the other. So probably a single neural network that which then sort of bifurcates into two would have been able to represent this as well.
I have a couple of answers to that. First of all, we are using this is rather interesting actually. Sequential means that there is no bifurcation. It's very simple to construct something which has two different outputs and to separate whenever you want the neural network, wherever to have the two different outputs. It is true that the lower levels of lower layers should find in a sort a feature extraction, in a sense that they should recognize what is important of the state and what is not. And so it could be beneficial to have them together. What it does, which was not exactly what I was talking before, it's of course, it will change. If you have an action, the update will change the value also for the other action. Which is fine. So let's say that I have right now what I meant with action, with the fact that we are tabular in action is that what happens in action A stays in action A. So of course, since we have value approximation, what happens with a state could change for certain will change the value for another state, but will not, this change of parameters will not change what is the approximate value for another action. if you use a single neural network, even if it's sharing only a few feature layers below, for sure it will be that the two actions will be speaking together, which then brings the fact that it's a value approximation in both state and action. It can be done, should be done, most probably, will perform better, but it added this fact that it's not an approximated only in state. So I wanted to keep it separate.
Okay, thank you. That's great. Thanks.
Okay. This is how it performs. So I did only 300 episodes, and I will show you why. And it actually performs very poorly. And you can understand why. I mean, the best model so far had a 6 space, right? It was binning 1132, so it had 6 different distinct space of which he wanted to find the policy, and it took several hundred episodes to find it. This method is clearly much more intelligent, but it's much slower at this point, and has 400 parameter space of very large. Okay, so this is, as I said, this is the worst implementation of the neural network inside the reinforcement learning which you will ever see in your life, I hope, for several reasons. What is normally not done as such is this. It is true that this method is on it's a stepwise method. You can apply every step, but first of all, it's extremely costly to call for the fit function, and do it for only one. It's a bad idea. Also, since the parameter space it's very large, generally speaking, what it's done is that you collect a batch of many single steps. So you will have, instead of having one single step update, you have first a part in which you collect all the states, all the new states, all the actions. Then at certain point, okay, I collected enough. For all of those, you will calculate the targets, and then you will have a much larger list of state, actions, new state, rewards, which leads to target. And then you will give it once, and then you can do it many things. So maybe you will run through it many times, randomizing the order in which you take them, essentially, or you will have to do a lot of other technical things. So this is the closest implementation with a neural network to what we have seen, for example, with a linear approximation. Essentially, it's the same thing, but instead of a linear approximation, we use a neural network. So this is why I'm wanting to say, I strongly advise to go to any tutorial with neural networks and reinforcement learning and see how it should be done on a technical level. But on a basic level, this is what it does right here. Yes, so I wanted to add in 2 minutes to what Antonio was saying before, that because I recalled that, so Antonio was saying that there is perhaps you need some. Once the expert advice was everything, and so you relied heavily upon that. So the first, I will perhaps be a bit imprecise, but the first programs to play chess automated were actually a lot of features were constructed by by expert players, and etc. etc. So once everything was a priori created, the features were created by experts, and it worked, and it worked quite well, and the way to planning and programming worked against human players, but it had relied heavily on human advice. Then I just saying, because I recall some expert, I forgot one of the leading expert in this technological application of a neural network, we said one of the things which I had to deal, which scared me in a sense, I'm paraphrasing quite heavily, is that I had to abandon the fact that my intuition as an input to machine learning helped the machine. In the end, given sufficient amount of data, sufficient amount of time, the machine, without my advice, without my expertise, worked better. So I think it's nice because I think there is a scale. If you want to solve a technological level at your level, then human advice, human intuition or physical intuition, it's definitely important. But I think that at the highest level of AlphaGo and things, then I think that there it's already where high volume enough of data and everything crashed the human expertise. I'm not sure if, yes, I wanted to give you a word even without the raise the hand, please.
Yeah, thank you for bringing this up, because I think it's very important. So, I totally understand what you were, the sentence you were quoting. The point is that the objective here was performance. So the researcher you were talking about was saying, if I remove my input, then my system has a better performance. But we always have to deal with multi-objective optimization. So performance is one axis, but then you have to ask whether it comes at compromising explainability. So your understanding of what the thing is doing, right? And then there is where the trade-off is. So if you accept to give up knowing what the system is doing, so if you're interested in having a black box which is giving you high performance, then of course your intuition might hinder the problem. And we see many examples of this. We see in applications that if you run a multi-agent reinforcement learning system, you can discover things that you didn't think about, okay? So there's an enormous power in that, but also there are limits to explainability. So, and clearly the other side of the spectrum is where you want to have a system which is as clean as possible, and then you have to put a lot of expert advice, and many times you get a negative answer from your system. So performance is poor, which is giving you something understandable, is the fact that your attempt sucks, you made some error, but it's an interpretable feedback from the system. So clearly, there's a lot of room in the middle, which one has to explore. But I think that it's a bad idea to make a strawman argument in favor of either full automatic learning or either full modeling without using machine learning as a tool. Is that fair enough?
Absolutely. And with that, if nobody has question, I would also conclude.
I have a question if I
yes,
can.
Please.
Maybe one curiosity. So the amount of hidden layer that you used for your neural network, yes, did you choose that number with some criterion, or is only?
No, I did not use any criterion.
But there is some correlation between increasing the number of hidden layer and the increasing of the performance of the.
Very roughly speaking, I know that I mean, let's keep the number of parameters fixed. Okay, so let's make strangely different neural network with the same number of parameters. If it's too shallow, if it's one layer or two layer, one layer, a hidden layer, it's been demonstrated that it's, even if it should work, it does not work. So performance has been shown to get better and better when the neural network becomes deep, and deep means that it has more than what I use. Start to have up to tens, I don't know. different layers. Okay, so if there is an idea that a neural network works better if it's deeper than it's shallower, because as Antonio mentioned, it turns out that you can clearly see that the lowest layers learn basic feature and construct on those basic feature and only the upper layers need to do the task. Okay, so it turns out that the lower part of your neural network is actually feature extracting in a sense, and then the upper part is learning to do what it must do. But with great power, great responsibility. And it turns out that if you do not do anything, so if you do not do any technical tricks, if you have deep layers, features, weights start to explode, or even worse, start to go to never update. Because this is a chain of gradients, and some of these gradients are zero because of the ReLU function. So at a certain point, you have a total percolation of zero updates. So if you do not do anything and you start, okay, I just want something narrow but long, narrow but deep, then you start having issue with convergence, with exploding gradients or zero gradients or stuff, and then you have to solve it with technical issues, and etc. So I choose 2 hidden layers because it's a compromise, and also because the problem is very simple in the sense that we saw that the solution actually requires to discard the first value, discard the second value, know only if the fourth value is positive or negative, and the third value should be just that if you have a quadratic formula and you have a cutoff, it's already fine. So I used 2 hidden layers, which is something actually 2 or 3 hidden layers is something which you will see most of the time as something which is a neural network and not a linear operation. But so it has some depth, but it has no real problem in working without using any technical tricks.
Okay, and another one, if I can, maybe to Professor Celani, because before you mentioned about
some time just to add something to this first question.
Okay, yeah.
We can go on to the second one. So that you don't believe that we are not losing good habits. So with every question comes an exercise. And the exercise here is actually particularly interesting because suppose you have a neural network with sigmoid functions, okay, not ReLU. It's just something which approximates a step. Now, if you combine 2 sigmoids, you can make up a box. So a simple linear combination of 2 sigmoids, one that goes like this, and the other one which goes in the other direction. If you combine them, plus and minus, you can make a box. So actually, if you combine linearly these functions, you can construct state aggregation. It requires just a few nodes. You see that? I don't have to picture, but think about just 2 nodes, which one takes the one real input and makes a step function. The other one takes the same input with a different offset and the minus sign. It makes a step function in the other direction. And if you combine the 2, you can make a box. Okay, it's a very simple exercise in combining transfer functions to make a sigmoid. So you actually, with few nodes, you can construct exactly the boxes that Emanuele was talking about, in which you were partitioning, making state aggregation. So actually, there is a minimal neural network which does exactly the same job as state aggregation and should be able to learn an optimal policy with very few nodes. So while I say that the statement by Emanuele in general is correct, so deeper network have a larger expressivity. So if you're looking for complex forms of your Q function, you should have deeper networks and wider also, etc. But in this particular case, you could make it work with a different choice of transfer functions and specific weights, which you can almost compute by hand, given the fact that you know that there is one particular state aggregation that works. Was there anything else that I wanted to say? Oh yeah, maybe I don't know if Manuel wants. Do you want to comment later on the code that is available in which you take images of the cart pole and then Manuel agree to do that?
Yes. Actually, it's not. It's not taking images. I will share. So this was a previous exercise in which one use neural network with deep Q learning. So it's slightly different, and it's an exercise which actually works better in the sense that it arrives to a much better solution. It's clearly much more complex. This is not done by me. I have to credit the previous person who did the exercises. And I will share it. And I wanted to also do, this is a much better, it's a step forward in a way in which neural networks should be used for reinforcement learning. I choose not to do this and do what I present, just because then you have the idea of exactly what changed where to arrive to a nonlinear functional approximation. And this is written much more closely to what it's done in technological sense. You see, for example, there is okay, the neural network is the same, but then the brain, so the algorithm, it's as a, of course, an act, as a remember, so it has to way to store information, trajectories, and then have a train, which is rather long term, and so it's written in a different structure. I wanted to present at first something which is in the same structure as we always saw. But then here you should be able to read it and understand what are the parallels or how to use in a better way. So, yes.
So there was a second question then.
Yeah, when you mentioned multi-agent, do you mean what exactly do you mean? Do you mean by parallelizing the problem and the train, or what exactly?
Who said multi-agent? Did I say?
Yeah, you mentioned before when I don't remember exactly. After one question, I think. Yeah, maybe or I don't know, or maybe if I can tell it better. So this type of problem can be parallelized then to combine the result and
so I must admit I don't remember when I said multi-agent today, so I'm not sure I can be very helpful. So there are things that you can do. I mean, I'm just picking up the buzzwords that you say. So parallelizing, yes, you could be doing several trainings together and then collect all the information into a single Q function, be it tabular or represented in different ways. This is something you can do and speeds up learning for sure. It is also a way to do exploration by combining different, and by sort of doing ensemble exploration rather than you making exploration in time. Yeah, I'm not sure I'm picking up the right question here. What I can say is that next week we will be doing multi-agent reinforcement learning. So we will take a view on this from
okay.
multi-agents.
Just one thing. Before I was talking and it made no sense because I thought I was sharing, and I wanted to show that. So there is another exercise which I will share with today's notebook, which you can use and look up if you want to see a better version of reinforcement learning with neural network. I apologize. I thought I was sharing. Okay, so we are running late again, so I will stop recording.